All right, guys, so today we're going to talk about spherical and cylindrical coordinates. And so let's go go ahead and start drawing. So let's do our three-dimensional grid. So X, Y, Z are three axes. And you remember before, whenever we had a point, or a vector, let's call it if you want, we had our entries X, Y, Z. These coordinates are called rectangular coordinates because they satisfy the, well, you measure them rectangularly, meaning you go and form right angles. Well, I didn't quite get it. I should have gone down first, I suppose. And you get your coordinates, right? So now we're going to do a little bit different. So for 2 dimensions, we had talked about polar coordinates. So whenever you have 3 dimensions, you can do kind of the same thing. And so that's going to be the idea of spherical coordinates first. So we're going to leave Z where it's at. So my Z height will remain there. So that one is going to be there. And now I got to figure out, when I project strictly down or straight down, I'm going to have a point down here that it would be, if you were to do the 2-dimensional point, it would just be the point with coordinates x, comma, y. So if you grab this xy plane and you draw it right here, so you have your point right there, okay? And what you can do then is that point has entries x, comma, y. But you can always go ahead and think about it in terms of the polar coordinates of it. So r and then an angle theta. So that point x, y, z, you can convert. I wrote it as a vector right now. I'm writing them as vectors. Really, I could use parentheses. I should use parentheses. But you can make it be related to, I'm going to do parentheses on this one, and r, theta, and then z. So these are going to be called spherical coordinates. So what you're going to be doing is you're going to be projecting down or up to the xy plane. And then on the xy plane, you do the polar coordinates for it, and those are going to be called spherical coordinates. So let's take a look and write what equations those are satisfied. Let's convert back and forth between coordinate systems, and then once we have done that, we're going to introduce the spherical coordinates. So right now we're doing cylindrical. Let me erase and do a few examples. So let's say that the points or coordinates, let's do x, y, z in rectangular coordinates, and the point r, theta, z in spherical coordinates. I'm not going to write that, but this should say in rectangular coordinates and this in spherical coordinates. And I should probably say the triples correspond to the same point on the space. If and only if, and we're going to have the relations. Well, what are the relations? So if and only if, let's write if with 2 f's to write if and only if. Well, firstly, you're going to have that x is going to be equal to r cosine of theta. Y is going to be r sine of theta. And z is going to be equal to z. So this is how you would obtain the rectangular coordinates if your spherical coordinates were given. On the other hand, if you know the rectangular coordinates and you want the spherical, I said cylindrical, sorry. If you have the rectangular coordinates and you want the cylindrical, what you would do is you write r is going to be the square root of x squared plus y squared. And then theta is going to satisfy the equation that the tangent of theta is going to be y over x. And since I chose my radius to be positive, let's keep that angle in between 0 and 2 pi. just so that we have a unique representation, and then z stays as z. So let's go ahead and do a few points, convert back and forth. Let's convert maybe an equation or two, and then we're going to move to spherical coordinates real quick. All right, so let's move here and do the examples. Let's try to keep the equations so we can use them. All right, so let's go ahead and convert 2 points from rectangular to cylindrical. So in this case, we're going to have to use this equation. So this is just doing polar all over again, because z is going to remain the same. So what you're going to be doing is you're going to write the radius is going to be your square root of 1 squared plus 1 squared. So grabbing x squared plus y squared, it's going to be square root of 2. And your angle, tangent of the angle, is going to be equal to 1 divided by 1. And that's going to be 1. So the angle that you're talking about, if you draw it, is going to be the angle pi over 4. So we're going to then say that this point corresponds to, in cylindrical coordinates, to square root of 2. Pi over 4 is the angle, and then z remains the same. So that one, very straightforward, because we've already done polar coordinates. All right, so here your radius is going to be, for the next one, the square root of the sum of the squares. So -3 squared plus 4 squared. And you know that this is 9 plus 16, 25. Root of 25 is 5. Yes, I picked up Pythagorean triplet to make my life easy. However, I need to do that the tangent of the angle is going to be equal to 4 over -3, so it's going to be -4/3. Now this one is not a point in the unit circle, but there's more to it. You cannot just say, well, I'm taking the arctangent and I'm done. Unfortunately, that's not going to work for you, but we can work on it. So I'll have to do a little graph over here so you can see what's going on. So this, if you just do the xy plane, it's going to be on -3, +4, so it's on your second quadrant. If you do the arctangent, remember the arctangent will give you the values on this interval from -pi/2 to pi/2 with respect to the angle. So whenever you plug this -4/3 into the arctangent in your calculator, that's going to give you an angle that corresponds to the fourth quadrant. So that's not the angle you're looking for. So you're going to do your arctangent. It's going to be somewhere here, and you're going to have to add pi to it so that you go to the correct angle. So remember, it's not always just taking the arctangent. So theta is going to look ugly, but let's say it's going to be the arctangent of -4/3 plus pi. I'm not going to calculate it. You can put that in a calculator, get an approximate value for the angle, but that would be what you would obtain. And then you do 1 for the z, because the z doesn't change. All right, so we're now, to convert backwards, I think I'm not going to do, because that is just plugging things into the formula. There's really no nuance to it. It's just use your formula. So if I give you something in cylindrical coordinates, you just plug it in, and then you get x, y, z. But let's go ahead and convert equations. I think that's a little bit more exciting. So just to keep the formulas here, I'm going to erase, and I'm going to come back. All right, so let's convert an equation into cylindrical coordinates, and you see how things work out. And usually you're going to do cylindrical when things, when the equations depend on x squared and y squared, like they do here, and also whenever you don't necessarily have z squared. If you have z squared, we're going to talk about that one later. So this case is pretty typical for cylindrical, because this right here is just the r squared, and this is -2r, and then that's going to be equals to 1. So if you plot this into your Desmos 3D in this form, what is going to happen is you're going to see what cylindrical coordinates are all about. All right, so now let's talk briefly about spherical coordinates. Otherwise, the video will be way too long, so I'm going to just introduce the coordinate system. We're going to convert from rectangular to spherical, and from spherical to cylindrical, just for points. We're not going to do equations because I don't think we have time for that. So again, let's go back to our same situation where we have a point. Let's put it somewhere out here. Now this time we would have projected down to do our cylindrical coordinates. However, this time I am going to do something slightly different. I'm going to draw the radius. So I'm going to say that this point, and let's write it as x, y, z in our rectangular system. So let's go ahead and look at what happens, or what the difference is. For spherical coordinates, I'm going to measure this distance. I'm going to call it rho. So by the Pythagorean theorem applied twice, I have that rho squared is going to be equal to x squared plus y squared plus z squared. And that's why when I had my other example, I said if you had a z squared, then you don't prefer cylindrical coordinates, you prefer spherical coordinates for that reason, because that just becomes rho squared. So if you take a square root on both sides, then rho is the square root of, I'm going to take the positive square root, and that is going to dictate what kind of angles we're allowed to have. So pick that one to be positive. So we're going to still do theta. So we're going to project down here, and I'm trying to decide what color I'm going to grab. So down here, I'm going to have the same angle theta that I usually would have, that starts at the x and goes to the line. So quick reminder, in the xy plane, such as right here, your angle theta is always measured from the x coordinate all the way out to the ray that starts at the origin and ends at the point. So the angle theta is measured in the same way. So theta is still going to be the same. So in that case, theta will satisfy the equation that the tangent of theta is still going to be y over x. So that is still the same. But now we don't have z equals z. That's going to be the distinction. So our z, because now we don't have the radius r, we have the radius rho that goes all the way to the point, not to the projection. Now we need another angle. And that angle, I will try to see if we can see it in blue. Oh yeah, we do. It's going to be called phi. Barely, but we can see it. So phi is going to now satisfy that z. If you look at this triangle right here, z is going to be equal to, and I should do it in the opposite order. Well, let's write it out now that I wrote it in this order. Z is going to be rho times the cosine of the angle phi, because it is, z is the adjacent to this triangle here, okay? To that angle there, sorry. All right, so, but this is kind of backwards because I was writing all the rho, tangent, and then z, so I should have written it like rho cosine of phi is equal to z. So if I have x, y, z, I can find rho. Then with y and x as before, I can find theta. And then once I have rho and z, I can solve for the cosine of phi by dividing z over rho. So you do have to calculate it in order. You have to first calculate rho, then you calculate your theta, because, well, that's the second one, and then you can calculate your phi. Now, cosine of phi. Now, this we can calculate straight up with the arc cosine. Why? Because the arc cosine will spit out values between 0 and pi, and that's where we want our cosine phi to be. So this one, we didn't even have to write cosine of phi equals that. We could straight up write phi is the arc cosine. There's no problems there. The only one you always have to be careful with, theta, just because, well, the arc tangent will just give you values between negative pi and pi. That is because the tangent is just pi periodic, it's not 2 pi periodic, so we don't get too lucky with that one. And so now let's write the other kind of equation. So this is the case whenever if you have rectangular, how do you convert to spherical? So now let's go from having spherical to rectangular. All right, so you gotta be careful with this one because z is easy. Z you get from this equation, so that's done. But x and y have to be a little bit careful. Why? Because you would say, well, in polar coordinates, x is just the radius times the cosine of the angle, and y is the radius times the sine of the angle. And that is correct. But that radius is r down here, and r, by looking at this triangle right here, because you're projecting 90 degrees, r is nothing but rho times the sine of the angle. Because notice that the angle phi here, you can also move it over here. So whenever you do rho times the sine of the angle, you get r. And the angle is phi, by the way. So with that, now that you have r, you can use that to write happily your x as r cosine of the angle, but r is this. So rho sine of phi cosine of theta. And y is rho sine of phi, that's r, sine of theta. And then z, as we said, was just rho cosine of phi. So that's how you go from now cylindrical to, from spherical to rectangular. And then the next step, or the next question is how do you go between spherical and cylindrical. So we'll do that in the next one. So let me go ahead and do one example. And I think I'm going to finish the video there because I don't think that we have time to do it all. All right, so I'll erase here and I'll do one more example. I'll be right back. All right, so let's go ahead and convert from rectangular to spherical coordinates. So that's when you use these formulas right here. So let's go ahead and do rho first, and rho is going to be the square root of 1 squared plus 2 squared plus negative 2 squared. So x squared plus y squared plus z squared. This is going to be 4 plus 4, 8 plus 1, 9. And the square root of 9 is 3. Yes, I fixed it so it would work that way. So my radius is 3. So the spherical coordinates, by the way, are in the order rho, theta, phi. All right, so theta, you see you have 1, 2. That is in the first quadrant. So this one you can obtain directly from doing the arctangent. So it's going to be just the arctangent of 2. 2 divided by 1. So I'm just using this. But I'm in the first quadrant, so I can just straight up take my arctangent. So great. So I'm going to write that. Let's just write theta because I don't have much room, but that's what the value of theta will be. And then to find phi, I have to do the arc cosine of z, which is negative 2, and divided by 3. So this is going to be the arc cosine of z, which is negative 2, over 3. And sorry about my space there. I didn't quite fit it. But that would be, those would be your coordinates. Of course, plotting or plugging in the values that you obtain. Now let's do this one real quick. So now the radius, rho, is going to be the square root of negative 3 squared plus 0 squared plus 4 squared. So I chose that to be another Pythagorean triplet. I put 0 because I couldn't think of anything more fun. How boring. So 9 plus 16, 25. Square root of 25 is 5. So here, rho, I start with 5. Now for the angle, let's draw this over here. You're going to be at negative 3, comma 0. So that's going to be your angle is pi. You don't even have to compute that one in the xy coordinate. Now I need to do phi. That angle, that was theta. Phi you do need to compute. And phi is going to be the arc cosine, using this formula here, of z, which is 4, over rho, which is 5. And that is just something we would plug in our calculator and plug in here as our coordinate. So that's how you convert in one direction. Now let me go ahead and give you points in spherical coordinates, and then we will go backwards. We're going to go to rectangular. And then the last thing we're going to do is we're going to change the equations here to go from spherical to cylindrical.